Power spectral density of a line code is dependent on two parameters. One, the autocorrelation of the discrete sequence corresponding to a particular line code, and the other is the pulse shape which is reflected in terms of Fourier transform of the pulse PT. We had derived the relationship for the power spectral density as follows. Where Pt is the pulse which you choose for your transmission and its Fourier transform pair is Pf, Tb is the pulse duration, and Rn is the autocorrelation function of the discrete sequence alpha k, which is the amplitude sequence corresponding to the choice of a particular line code. Now, we see from here that power spectral density is strongly and directly influenced by the choice of Pt, because it contains the term Pf mod squared. So, the pulse shape is a more direct and important factor in terms of shaping the power spectral density. We have seen that this power spectral density theoretically extends right up to infinity. So, the theoretical bandwidth of a line code is going to be infinity, and usually what will happen that these signals are being transmitted on a band limited channel. Now, because of band limited channel, spectral distortion occurs and this tends to spread the pulse. This is also known as dispersion. So, spreading of a pulse beyond its allotted time interval, that is Tb, will cause it to interfere with neighboring pulses, and this is known as intersymbol interference and popularly known as ISI. So, it is important to know that ISI is not noise, it is caused by non-ideal channels that are not distortionless over the entire signal bandwidth. So, ISI is a manifestation of channel distortion. To resolve the difficulty of ISI, let us review briefly our problem. So, we need to transmit a pulse every Tb interval. So, the kth pulse is denoted by alpha k Pt minus Ktb, and it is required to detect the pulse amplitude alpha k, that is without ISI. Now, in our discussion so far, we have assumed that our pulse Pt is time limited. Now, what this implies that it will have infinite bandwidth. Now, when such a pulse gets transmitted on a band limited channel, the pulse Pt itself will get band limited, and this will bring about pulse dispersion, that is ISI. So, let us try to solve this problem by choosing a PT which is band limited, so that it matches with the characteristic of a band limited channel, but then this implies that PT will be of infinite time, which implies that there will be pulse dispersion, and again you will get ISI. So, irrespective of the choice of PT, either you choose time limited or band limited, on a band limited channel you will always get this ISI. Now, it is important to note that we are interested in the pulse amplitude alpha k. So, pulse amplitudes can be detected correctly despite pulse spreading if there is no ISI at the decision making instance, and this can be accomplished by a properly shaped band limited pulse. So, to eliminate ISI, Nyquist has proposed 3 criteria for pulse shaping. And this criteria allow the pulses to overlap. In spite of the overlap, they are shaped such a way that they cause 0 or controlled interference with all other pulses at the decision making instance. Thus, by eliminating the non-interference requirement only at the decision making instance, we eliminate the need for the pulse to be totally non-overlapping. So, we will study only the first 2 criteria. The third is much less useful than the first 2 criteria, and therefore, it is not studied here. So, let us try to understand this ISI problem little more in depth. So, let us say that we have a pulse, we choose a rectangle pulse, and that pulse is to be transmitted on a communication channel which is of a low pass nature. So, let me model the channel to be a simple RC circuit shown here. So, the output of the encoder and impulse modulator pass through a filter which generates an appropriate pulse of height alpha k is input to the channel at this point, point A, and you get output of the channel B. So, let us see what will happen if I apply a rectangle pulse at point A. I have a rectangle pulse of duration Tb of height V, and it is easy to see that if I take a low pass filter, the output would be something like this. If we have more than one rectangle pulse in sequence, then let us see what will happen. And this figure depicts that scenario. So, here I have shown 5 pulses, and these are the pulses which is input to the communication channel, and these are the outputs which I get from this communication channel corresponding to each of the pulse. So, if you look at this interval, that is between 3 TB and 4 TB, the signal which we receive at that time would be summation of all the previous pulses and the current pulse which has been transmitted at time t equal to TB. So, if you look at this instant, any instant between this to this, and if you were to sample the point, so this is your 3 TB. So, if you sample at this point, you get contributions from other previous pulses, though the contribution from this and this is much lower compared to just the previous pulse. But in principle, you get contribution from all the previous pulses at this instant of time. We will try to model this digital communication system as shown in this figure. So, I have an encoder. The encoder output is usually the binary stream, and this binary stream is passed on to the impulse modulator, the output of which are the amplitudes alpha k, these are impulses, and then this impulse train basically is fed to a filter HTF, this is known as a transmitting filter. So, if we choose the impulse response of this filter to be a rectangle pulse, whenever I apply a input impulse here, I will get a rectangle pulse as the output of this filter. Correct? So, this is how you can generate at this point the appropriate line code by choosing appropriate value of alpha k. So, then this output of this filter goes to the channel. This is the point B which I have denoted, and this was the output which I had shown earlier at point P. So, this is the same as what you see here. Okay. Then on the channel we have noise added to it as WT, usually you will choose as additive white Gaussian noise. Then at the receiver we would have a receiving filter. So, in the absence of say HCF, like if you choose HCF to be equal to 1, then your HRF, for we have shown that for additive white Gaussian noise, this would be a match filter to the pulse which is coming out at this point. And then we sample it, and then we use a decision device to take the decision of the amplitude alpha k, and then accordingly we find out which message has been transmitted. So, we will assume that here we have, this is your YT output, and this we can call it is the RT. So, this RT is what I have shown here. Okay. So, in general, let us write down the received signal at the output of the receiver filter. So, YT would be equal to summation alpha k p t minus k TB, k is equal to minus infinity to plus infinity plus eta t PT is basically the convolution of the impulse response of the transmitting filter with the communication channel impulse response convolved with impulse response of the receiving filter. So, this is the overall response of the system due to a unit impulse at the input, and your eta t noise is Wt convolved with the impulse response of the receiving filter. Now, without loss of generality, let us assume that P0 is equal to 1. Now, at the sampling instance, I am going to sample this. So, at the sampling instance NTB, I am going to get the output from here equal to alpha n plus k not equal to n plus eta sampled at n Tb. Now, this portion out here, this portion corresponds to your ISI, intersymbol interference. Now, we will look into the conditions on the overall transfer function, which is given by Pf is equal to HTF multiplied by SCF channel transfer function multiplied by receiving transfer function. We will try to choose this Pf in such a way that we get ISI to be 0. Okay. So, let us try to understand when we will get ISI to be 0, and we can do that with the help of this figure out here. So, here I have shown Pf, which is the overall system transfer function composed of these 3 filters. If I apply input impulse of unit strength, then the output I will get will be Pt, and the Fourier transform of this Pt is Pf. Okay. So, what we expect that if there is no intersymbol interference, then when I apply the impulse at t equal to 0, I should get output at t equal to 0, and all other sampling instances this output should be equal to zeros, right from minus infinity to plus infinity for all values of Tb n multiplied by Tb except for n equal to 0, this value should be 0. So, if Pt is such that this is the case, then the system will experience no ISI, since an impulse say at t is equal to m Tb will produce a non-zero value only at that time t equal to m Tb and 0 at all other sampling points, correct. So, this is the time domain condition for no ISI, and this is known as Nyquist first criterion for 0 ISI. So, it says that choose a pulse Pt such that Pt is equal to 1 for t equal to 0, and it is 0 at all sampling instances, which is denoted by plus minus NTB, where your TB is equal to 1 by RB, the rate at which we are transmitting the pulses. Now we know that for transmission of RB samples per second, we require a theoretical minimum bandwidth would be equal to RB by 2. So it would be nice if the above PT had this minimum bandwidth of RB by 2. So the question is, can we find such a pulse? And the answer is very simple. The pulse which will satisfy this is the sync pulse and the PF for this what this means is a rectangle function of a duration RB about f equal to 0. So the function PF is shown here in this figure. It is a rectangle function and the time domain signal corresponding to this PF PT is a sync function. So if you choose this, then we see that only at t equal to 0 you get the value equal to 1, whereas at all other sampling instances the contribution from this pulse would be equal to 0. So there is no ISI in this case. Now there are two problems with this, with the choice of this pulse. One, the above PT is impractical. Why? Because it is non-causal. It is existing from minus infinity to plus infinity. The other problem is that when we are sampling, when you transmit such pulses and when you do the sampling at the signaling intervals, the pulse amplitude will not vanish at the other pulse center if this sampling is not done exactly at plus minus NTB. So if you have a small deviation there, it will contribute to other pulses, correct. So let us see this. So we know Yt is equal to summation alpha k p t minus k tb, k equal to minus infinity to plus infinity. Let us say that instead of sampling at t equal to 0, I do the sampling at y is equal to delta t, where delta t is small. Now what would happen? This would become this expression here. So k is equal to minus infinity to plus infinity. So I will not write it here, it is presumed. So let us try to expand this. We have chosen the sync function. So this would be equal to sine of pi I am just substituting the value in the sync function. This I can rewrite it as summation over all k's alpha k. Let us expand this. minus cos of sine of pi k whole thing divided by pi delta t minus k. Let us see what we get. The other term here will go to 0 because of sine pi k. This I can rewrite as and this quantity gets multiplied by the quantity which I am writing below here. So, this is a k equal to minus infinity to infinity, but k not equal to 0 because this has been taken here. So, this is equal to alpha k delta t divided by Tb minus k. Okay. Now, this term, the last term out here, this is not absolutely summable. So, because of this, the pulse decays, because this pulse decays only as 1 by, if you look at this pulse out here, the decay of this pulse is 1 by t, and if you have this mistiming of the sampling, then this is the cumulative interference at any pulse center from all the remaining pulse, and this does not converge. Right? So, now the next question is it possible to find Pt which satisfies Nyquist's criterion for 0 ISI, but decays faster than 1 by t. Now, Nyquist has shown that such a pulse exists which has a bandwidth lying between Rb by 2 and Rb, and we will study this case in the next class. Thank you.